All right, so we're looking at our Chatelier principle worksheet. And we're looking at the idea, okay? And I don't know quite where I'm on. Okay, we go. Looking at the idea that we've got reactions that are reversible or have some reversibility. Now, these are not, some of these are redox reactions, some are not, but these aren't examples of Voltaic cell. So the Chatelier principle is something that permeates throughout all of chemistry. If a reaction is, or a process, reversible, then what we're talking about there is a competing pathway allowable by nature. Bottom line is something can reach equilibrium means that both pathways are possible, okay, allowable by nature. As we're going to learn later in the year, there's going to be some reactions that are not, okay, reversible. Not all things can reach equilibrium. So if something can reach equilibrium, like a battery, when a battery reaches equilibrium, what's its voltage? Zero, because you're at basically the death of the reaction. You're at the lowest free energy. We'll talk more about that. So if I give you a reaction double arrow, I should be able to do these things. I increase N2. N2 is what chemists do, and we use the Chatelier principle, but I don't want to lose sight of what really it is. Okay, here is my reactants, 100%. Here are my products at 100%. This represents the death. Now I'm showing 50% products and reactants. Equilibrium really isn't 50%, but just for simplicity. So if I was to increase the amount of products, hey, the percentage of products are higher than normally at equilibrium, then I'm in this position. This means that there's going to be what? Some pathway that is now more possible in the reverse than the forward. We are now competing with the forward. The forward's spontaneity is now going to be limited because you're increasing the what? Spontaneity of the reverse. So, by increasing, and this is the stress that we as humans do, by increasing the N2, what you're really doing is you're going to force the reaction to shift in the reverse. So we say shift to the left, okay? Beyonce shift, right? And so therefore, what we're going to do is, if I increase N2, the N2 is going to eventually go down. It's going to work its way downward as we work backward toward equilibrium. Do not forget, that's what this is about. This response is the shift. And the shift represents what? A now thermodynamically favored pathway is now increasing in the reverse, which is now limiting the forward. If this was a redox reaction, what would happen to the volts? What happened to the voltage of the battery? It would go, I'll give you two choices, up or down. Okay, I'm picking up some down. Good, all right? We have a one-way reaction. We need the anode to oxidize, go one way. So if you build up some reversibility, the voltage drops, okay? So it's important you get that because we're going to move this Chatelier principle to the Voltaic cell in a second. Easy for me to say, okay? So you have these. Now you can break it down into this, but you've got to make sure you understand what it really means. Now, the only thing that's different here is pressure. When you have pressure, you have to count the number of particles. There's 2 particles of ammonia here that are gases. And there are 4 particles, 3 plus 1. Nothing in front is 1. If I have an apple and I give you an apple, let's say I'm giving you 1 apple, right? So there's 4. And what do gases do? Gases fly around in containers, and when they hit the container wall, they apply a force. And that force is a pressure over area. The more particles you have, greater the what? Force. So, party people, if I increase the pressure on this system that can be reversible or reach equilibrium, the reaction is going to shift in a way to lower the pressure, and it's going to favor the side with less moles of gas. So anytime you have pressure values or pressure stresses, you have to make sure you have gases. If you don't, there's no effect. If the number of gas particles are the same, there's no effect. I did forget the 2 in the worksheet. So I'm not going to walk you through that, but you should be able to handle that. Now also last night's homework, or the weekend's homework, there's another thing called common ion effect, okay? For instance, and I'm just going to make it simple here. If I have A plus B, gives me C plus D. There's my reversible process. And let's just say I added a chemical, KC. And let's just say that breaks apart into a K and a C. I'm just making this up. There's no K in this reaction, so the K has no effect. But don't I have C in this reaction? So by adding a chemical that's delivering a common ion, what you're really doing is increasing that chemical. And if you increase it, what's the response going to do? Decrease. If I want to decrease C, and this is where people get confused, do I use it up to shift this way, or do I want to make more of it? If the response is to lower C, to work backwards toward equilibrium. To lower C, the reaction is going to shift to the left again. Okay, that means you're going to make this a reactant. These are products, and these guys get used up. Or you're working backwards there. Okay, we're making the leap of Le Chatelier's principle into redox. We're going to keep looking at this in different parts of the year. Okay, all right, enough of that. So let's go to the cell. All right, let's get out of this and go to what I had posted here for your notes or part of the lesson today. Okay, and so last week, okay, I had the Danielle cell, and just give me a second, I'm doing labs here. We've got this, and I'll put this on the video, and then I need some more zinc nitrate, because the other one is gone. Give me a second. Zinc nitrate is soluble, so I'll have to add some. Okay. All right, so we have zinc nitrate, and let me change the camera. All right, boom, okay, here we go. So here comes some zinc nitrate. I'm gonna pour it like a cook does. Okay, and it should dissolve, why?
It's soluble.
And what does that mean?
It means that the water molecules can go in.
The water molecules can compete for the ions in the crystal. Okay, so that should disappear nicely, and it does. Okay, now, I do have to change, a lot of my copper's bleeding in here, so I do have to change the salt in my salt bridge to stay with me as opposed to just leaving. Okay. All right, so I'm going to add, the salt in the salt bridge is sodium nitrate, which is made up of what ions? Na. And what's the nitrate ion?
Nitrogen and
helium.
nice, Kyla.
Well, that would be the nitride, but it's NO3, NO3 minus 1. And we're going to see it so often that nitrate NO3 is going to be 1. Many people like to make you memorize that, but just by using these certain ions over and over again, you'll get it down. Okay. Besides, you'll have an ability to see that. So, any case, so I'm going to put my zinc metal, which is also a little dirty. Just give me a second. My electrode here. Okay. A little bit of corrosion here, so we're definitely going to have some voltage drop. Okay. I'm going to set up my voltmeter at Christmas in July. Just put this around this way, and this one around this way. Okay, so let's get a voltage. Okay, anode goes to the black lead. We know that zinc is a little more what? A little more better at oxidizing. I'm looking for my black lead. Sorry, what happens when I'm getting classes in my other classes. Okay, so there we go. And I wanted a red lead. You could have stopped me right there. Okay, so right here. Christmas in July. Of course, it's got to be intertwined. Okay. Just did lab last period, so out of my mind. Okay. And we have no voltage. Why? No what? No salt bridge. And what does that help us get a voltage? That provides a pathway for electrons?
Yeah.
No pathway for
That's for the
ions to flow to maintain what? Electrical neutrality. What's happening? Mg0 solids becoming Mg aqueous plus 2. Plus 2 is building up in here. Why would electrons leave if this is getting positive? Copper plus 2 is jumping onto the copper of the electrons that have passed to it. become copper 0. You're losing copper +2. This beaker's getting negative. Why electrons move to a negative? We've got to keep these beakers electrically neutral. So you're killing this. By allowing ions to flow, the sodium and nitrate, we have a voltage. Okay? Hey, no salt bridge, no voltage. Salt bridge. Every battery must have one. Okay? Now, what do we do? Okay? Well, if you remember, I added water somewhere Friday. Where did I add water? Let's look at the overall reaction here. Zinc 0 plus copper +2. We've done this already, so I'm not going to break it down. Okay, it gives me zinc +2 aqueous ions plus copper 0. Anyone remember what I did Friday? I added water and the voltage increased. If the voltage increased, am I going to have a more spontaneous pathway in the forward or the reverse?
Forward.
Forward. This is going to shift to the right. Where did I have to add the water? Now remember, party people, adding water means I'm decreasing the concentration of some ions. Why? Well, the reason is I should be writing these ions like zinc +2 brackets. This means molarity. Molarity is a ratio of how many ions divided by how much water in liters in volume they're flying in. So if I add more water, I'm not taking out zinc +2, but I'm increasing the amount of water, so the ratio is decreasing. It's getting dilute, right? That's what this is. So if you remember, if I want to shift to the right, let's think about zinc. If I was to take zinc +2, and here's my stress, I decrease zinc +2. What's the response by the... You want to increase zinc +2. And how would I do that? Well, what would the reaction do to increase zinc +2? It would shift to the right. Because zinc +2 is a product if I go to the right, so I'll produce more. Okay? That's what I did. I added water here. And I added a stress. I lowered the zinc +2. I added water, and I made the reaction go more forward. There was a better pathway going forward. The voltage increased by added water. Now, what if I add water here? What if I was to dilute copper +2? Increase of copper +2 solution. Now, what shift would increase the copper +2 solution? That's right. You have to shift this way because now these become the reactants. These become the products, right? This would what? So people, when I said I added water Friday and I increased the voltage, I was being too vague. I added water to this half cell. If I add water here, I should be dropping it, right? Okay, so if I was to add some water, we can try that. Okay, we're manipulating and using our understanding of Le Chatelier's principle, but don't fall in love with just this box here. By me adding water, I'm lowering a reactant. I'm lowering the percentage of the reactant, which means that what? Products sort of have a higher percentage. You're going to work backwards a little bit. We're increasing the spontaneity of the reverse reaction, which is going to do what? Limit the forward spontaneity, and the volts should drop. Now, it's not going to be a lot, okay? But hey, I could try. This is just plain old-fashioned water. Very old-fashioned because water was made like what, billions of years ago. Okay, so here I go. Adding water here. And we got a little bit of a drop, okay? You with me? It did go up, up again. Okay, but we did get a drop. You saw that? I don't want to do it too much. Okay, now, what else could I do? All right, well, so Friday and today, I added water to decrease the ions to shift it. There's another way to decrease the amount of ions. You with me? Okay, so I want to pull this out for a second. It's going to go to 0. All right, and there's another way to do it, and that's what today is about. There's another way to lower, okay, the amount of ions, to call it, to add, besides adding water. Okay? By the way, there's another way to add more by adding a common ion. Okay, so this is what today is about. So we're going to go to this worksheet. I'm going to go clear in a second. Annotate. And And I'm going to pull this up. And here we go. Further frost. I guess I got to connect. I'm here. Just on my cursors. Sorry if I'm cursoring. Okay, cool beans. All right, so here we go. So here we go, chemical names. Forget the chemical names for speed. We're going to start with this reaction here, Ki. Okay, now, is Ki soluble? Is Ki soluble? Will it dissolve in water? Well, you guys are going to have this table F, Regents Chemistry table F here, okay? And, because you're all shy right now, let's look at our solubility rules. Now, we don't need them because K is +1, iodine's -1. What do I know about the size of the charges in Coulomb's law? Are they low or high? They're low. Okay? They're low. So party poopers. So anything with a group 1 ion like K, it's dry. Oh!
You see the plant?
Did I hit the plant?
Nah, you read my pass.
Oh, cool. Woo.
Alright, equal.
Yes. All right. So potassium is right here. It's a group 1 ion, so low charges. It's not going to attract the what? The iodine strong enough, so guess what's going to happen? It's going to dissolve. So party people, we write aqueous. AQ. Lead nitrate. This is so written so wrong. This should be NO3. This should be a 2 here. My bad. I feel bad. I'm over.
That's how it is on ours.
Is it? Okay. Anyway, nitrates. You might say, Mr. Grodsky, I don't know what a nitrate is. Well, you'll have these tables, but a nitrate is NO3 -1. That means this whole thing is -1. And because there's a 2, that means the whole overall charge of nitrates is -2. What must be the lead?
It has to be positive.
It's got to be +2. Mr. Grodsky, I don't see the charges above them.
It's neutral.
Exactly. The positives and the negatives cancel out, so you'll never see the charges. But you have to know that this is a salt. Both of these party people, okay, exist as a crystal. The positive is the metal. The negative is the green. Now, this is a monoatomic ion. This would be a cluster of 4 atoms that stick together, but it'd still be a crystal. Both of them have weak charges. And so Mr. Grodsky, lead +2 is high. Yes, but the nitrate's so small, the lead can't attract. But if you forget, nitrates are always soluble. You see a cluster of NO3s, party people, always soluble, which means coulomically, the attractions between the ions are so weak, water can compete and dissolve them. Okay, now, let's dissolve Ki. All right? And I'm supposed to have 2 beakers here, but I think I used them in my craziness. So, let's dissolve potassium iodide, which is the name. Remember, this summer we did naming. Potassium is the name of the metal. Iodide, okay, is the name. Iodide is the name of the salt. Or iodide is the name of the ion, the non-metal ion. Okay, so, I'm going to go here. Go back to where I was and change out this. All right, here we go. All right, we've got this. We're going to add some Ki, and it's a solid. A little cooking going on. Oh, there's my solids right there. A little more, a little dab will do you. Those are the exact measurements. Right, so there's my solids. Can't see through them because you can't see through a crystal. Okay, so I'm going to add some water. That'll do me. I'm going to dissolve. I'm going to stir and increase the surface area. And by doing that, we can watch the ions seemingly disappear. That's not true. It's just that you can't see individual ions. Water is doing what? Pulling them out of the crystal. I'm interconnecting everything that we've kept learning. We're not moving on, we're just using that stuff. So that's what aqueous means. The problem is, when we write it, that's a lie. Why is that a lie? They're not really together. So really in a beaker, I want you to draw it for me. what do I have in the beaker? I really have K plus and iodine negative. Now in truth, I do have the negative part of water surrounding it and the positive part of water surrounding them, but we have free ions. I think we learned about that. Okay, lead nitrate. Let's do this guy. Okay, so we've got another beaker. Ki goes to the side. And we're going to add some lead nitrate. And again, I don't need exact measurements. If we do a limiting reagent, we'll learn about who the excess chemicals are. Okay, good enough there. So there's a solid again. Okay, and I'm going to add some water. Although lead is +2, coulomically, it doesn't attract the nitrate very strongly because the nitrates have a low charge density. They have what? 4 atoms trying to hold on to a -1 charge. So the water can compete for the charges, and it looks like the positives or the crystal is disappearing. But we know better. The water is just grabbing them. Okay, we're almost there. Okay, and now I got my solution. So this is my lead nitrate. This is my potassium iodide. Okay. Now we're going to put this in a bigger flask. Let's put the lead nitrate here. All right. I'll keep these like there for a second. Now, because the lead nitrate dissolved, what do I really have? Don't I really have the lead +2 floating? Christmas. Lead +2 floating around, and I got nitrate ions. And I'll just keep their same ratio. Now, what's going to make? I'm going to pour these together. So, it just so happens that lead +2, just by chance, will hit an I- ion when I pour these together. Just by chance, hook and crook. You'll say, well, what's the big deal? Well, the big deal, and again, this is one of those exceptions, okay? Lead +2 and iodine. Well, you know iodine is a halogen. It's a -1. So you'd expect it to have low coulombic charges. Halogens are chlorine, bromide, and iodine, okay? So, what do we know? Being negatively charged, it's going to be soluble. However, there are what? Exceptions. Now you say, Mr. Grotsky, what are the exceptions? Exceptions mean that things in nature don't follow the rules perfectly. We often use rules to oversimplify. There's other things going on. Pb +2 is highly charged coulomically. Iodine is bigger in -1, but iodine also has a lot of electrons in its cloud. Okay? So having all those electrons in its cloud, okay, is able to actually really be bigger than -1. Just trust me on that. There's exceptions, and we'll talk about them. Bottom line is, normally this is soluble. Breaks apart as free ions. Whee! But when it hooks up with lead +2, is not soluble. What does that look like? What is that? It would be a crystal. So what I'm saying to you, party people, when I pour these together, I'm going to make a lead who's still +2, hook up with an iodine who's -1. This is not a redox reaction. But because iodine's -1, don't I need 2 of them?
Yes.
Yeah. So this becomes PbI2. I should draw it closer. Called lead iodide. And because it's not soluble, will it be aqueous? What phase will it be?
It would be solid.
Right. And we call this a precipitate. Precipitate is a word we use when something when a new phase is occurring. Hey, we say it's precipitating out when it's snowing or raining. it's liquid out. Normally it's gas. Okay? So that's a solid. Now, what else happens? People say, well, the K plus
With the
is a positive, hooks up with a what? NO3 negative. I put them together so the whole thing is 0. Now before we say, well, wait a minute, KNO3 is what? K is a group 1 ion, isn't it soluble? Nitrates are always what? Soluble. So this is aqueous. It's kind of a lie, isn't it? But there is your, let's balance. How many iodine ions do I have here?
E2.
2. Notice I only have 1 there. I can't change the chemical formula, I just put a 2 there. That gives me 2 iodine ions. Now I have 2 K pluses. I only have 1. I can't put a 2 here. I can't change the chemical formula, positives and negatives. So I throw a 2 there. How many nitrates do I have now? Or the distributive property? This is a cluster.
You have
This is 1. So now I have 2 of them, right?
Yeah.
And don't I already have them there? And I have 1 lead and 1 lead. We'll do more balancing, but I'm just showing you what's the overall reaction. But that's a lie. Because this is really separated. This is really separated, and this is together. That's the only thing that's actually truth here. But they write this reaction like this, which is called a double replacement reaction. The ions are switching partners. But that's a lie because they really weren't together because they're soluble in solution. Right? So what's in this beaker? You have a solution. We're going to have a solid on the bottom. I'm being artsy by drawing the solid off to the left. I'm kind of tilting it, right? If you tilt the camera and take a picture, you're artsy. I'm just being artsy, okay? So this is going to be what? The solid is on the bottom. That's PBI, 2. And the solution, what's going to be in solution? What's not dissolved? And what is actually staying undissolved? The K plus, right? And the NO3 minus. Now, how do we write this to make it look like to kid out the spectators? Did K plus ever do anything? It's free over here, it's still free. So why would I include it in the net overall revenue? Your net paychecks takes out your what? Taxes. So net ion. The nitrate was free over here, it's still free. The only 2 things that were involved is that a P plus 2 hooked up with 2 of these. So that's what we write. We take out the spectators. So what do we have? Pb plus 2, which was aqueous. And we needed 2 iodine negatives. And what did it become?
PBI.
PBI2, and what's the phase?
Solid.
Right, and that's your precipitate. That's what really occurred. The K plus never did anything. The nitrates never did anything. Okay? Let's go see it happen. Okay, I got lead nitrate. It's a solution, isn't it? Which means it dissolves. I got Ki. I'm going to pour the Ki into the lead. We don't need the voltage because there's no voltage here. So let's do it. Ready? And we should expect a solid to appear, correct?
Yes.
Let's see. Solids means you can't see through it. Now, how do I know it's a solid? Can't see through it. In fact, the solids are going to start to what?
Clump together.
Settle. What's on the bottom? What should be on the bottom?
Solid.
Yep, the PbI2. And this is eventually going to go clear because it's a yellow precipitate. It's a fantastically yellow precipitate there. And what's going to be on top? K plus ions and NO3. People will still say, hey, that's potassium nitrate aqueous on top, but you better know it's free ions. Okay? you still can't see through it. There's my eyeballs. Can't see it. Mad because I can't see through it because what I just made was what? A crystal lattice. Can't see through crystal lattice. Now, why did I show you this? Well, two aqueous solutions that do dissolve could possibly bring into play two ions that when you pour them together could form a precipitate. Now, how did I decrease the water in the Danielle cell? Friday and today. I dropped water onto one of the cells, correct? And by dropping the water, I'm increasing the volume of solution, but the number of ions are staying constant. The ratio of ions to water dropped. It got dilute. I can drop the concentration of any of the ions by doing something else. Didn't I take out the iodine by exposing it to lead? Is the iodine free anymore? So, if I deliver an ion that will precipitate it out, what am I doing to the concentration of the iodine ion? Increasing it or decreasing it? If I am taking a lead, and when a lead plus 2 hits an iodine, it makes it into a crystal. These ions in this crystal are no longer available. The concentration does what? Decreases. So by precipitating out, okay, as long as you use your rules, you can precipitate out the ion, and that will lower the concentration, and that will be your stress. Okay, not just adding water. Now, just like a cooking show, I did this the other period to show you how it settles over time. Okay, I don't know if but this is a better settling, I think. I don't know if it's clear or not, but tomorrow we'll look at them. That didn't work as well as I wanted to, but tomorrow we'll do that, okay? And I'll put a cover on that. All right, so let's go back to our cell. And let's precipitate out one of the ions and see if we can predict a voltage increase or decrease using the Chatelier's principle. You with me? Look at all the chemistry that's bound in here. Okay, I need a, let's see, I need a voltmeter. Cool beans, if beans are chilled. Okay. I need a chainsaw. Oh, I hear one. Okay. And I needed my other, where'd my two? Oh. Black lead. Well, this will go directly here. So we'll go, let's switch it up here. Keep zinc on left side to keep things simplified. Okay, here's my anode, cathode, for reasons we should be doing this at this point ad nauseum. Okay, and I had a red lead right here. Okay. And I have no voltage. Why?
There's no salt bridge.
There's no salt bridge to do what?
With the ions.
To allow the ions to flow that will do what? Oh, maintain electrical neutrality. I just erased something I need. Okay, so copper plus 2 gives me zinc 0. Zinc plus 2, sorry. Okay. That's the one-way reaction. Redox is one way. We don't want the opposite. Okay. Electrons are flowing where? From the anode. By the way, the anode is given to be negative because it's the place for electrons coming out, right? Piece of zinc is doing what? Oxidizing to become zinc plus 2. All right, zinc 0. Okay. Zinc 0 is going to what? Zinc plus 2, pushing out 2 electrons. I'm pushing electrons. And they're going to flow down here, and they're going to pull back here, and electrons build up. The copper plus 2, already in solution, does what? Gains them, become copper 0. Okay? Only when you have a what? Salt bridge on. Okay. Here's my salt bridge. All right. And there's my voltage. By the way, this is sodium nitrate. Na plus, NO3 minus. Over time, I'm building up zinc plus 2. I need the negative ion to come down in here to balance that off. Over here, I'm losing my positive. A positive replaced. Okay? Now, given all of that, by the way, they make the cathode positive. Why? By convention, electrons are moving toward it. All right. So now I'm going to use a soluble salt to do this. I'm going to use, and I'm almost done, I'm going to use sodium carbonate, called washing soda. What is sodium carbonate going to, by the way, is it soluble? Sodium is a group 1 ion, correct? Its charge is a low. So that's going to break apart into Na plus and CO3 negative 2. What is sodium carbonate delivering that potentially can precipitate something out? Isn't it delivering something with a high coulombic charge? Right. So here's what I'm going to do. I'm going to pour sodium carbonate into this beaker. I'm going to add carbonate ions. They're going to be free because they're soluble, correct? So what do you think the carbonate's going to do with the zinc plus 2, who's positive 2? A positive 2 and negative 2 coulombically are what? Coulomb's law. Going to attract each other so much that what? They're not going to allow water to separate them. You're going to make a what? A solid, a precipitate. And if I precipitate out the zinc plus 2, what am I doing to its concentration? I'm lowering it, right. So the stress is that we're going to lower zinc plus 2. What's the reaction going to do? Try to make zinc plus 2, and it'll shift where? To the right. So by me adding copper, something soluble, a solid's going to appear. And we should see an upward increase in voltage. It may not be fast. There's a competing problem here, and I'll explain in a second, but we'll give it a try. We should see it bump up a little bit. Here we go. I'm going to drop this right into the zinc, and you're going to see some solids appearing. Let me move this off to the right a little bit. This readily dissolves. So we got 0.85. Come on, don't make a liar of me. Making me a liar.
It's like a snow globe.
Yeah. But that, by the way, is precipitates. I do have a competing issue. Christmas in July. There is a competing problem. Now, the competing problem that I couldn't overcome, do you see this getting really blue?
Yeah, it's the.
Yeah, so here's what's happening. This is a higher concentration than here, correct? So this is moving by diffusion through here. Now, I didn't get that little bump because it's a competing problem. Let me explain. As I added this sodium carbonate, the carbonate negative hooked up with the plus 2 ion. And the plus 2 ion made it precipitate and lowered it to force this forward. So this process was actually lowering copper plus 2 and making it do what? Go backwards. If I didn't have this blue here, I'll try again tomorrow, it'll be a little blip, and I'll show you that video. If this was a test, you could say definitely that would have gone up. It didn't because this was leaking back, and I'll show you that video tomorrow. Have a great day. Didn't quite do exactly what I wanted to, but that's science.